thank you for your contribution.
Thank you very much. So my name is Lana Narine at Okay. My name is Lana Narine with Auburn University, the School of Forestry and Wildlife Sciences with Auburn University. And this study was carried out in collaboration with Dr. Sorin Popescu and Luisa Malambo at Texas A&M University. I know there was a discussion already about ICESat-2. Over the course of the mission, it will provide a grid of measurements over the Earth's surface. One of the mission's data products is the ATL08, or Long Track Vegetation product, which will provide terrain and canopy height estimates, canopy parameters at a fixed step size of 100 meters in the along track direction. The purpose of this study was to examine ATL08-like data. It started before the launch of ICESat2, so we used simulated data for this study. Ongoing work involves the implementation of methods with actual data, but for this study we used simulated data sets. So the goal was to create wall-to-wall maps of above-ground biomass using ATL08-like data in conjunction with other spatially comprehensive data sources. This is a study area located in the Sam Houston National Forest. That's in southeast Texas, and about 48 square kilometers. The area is predominated by pine plantations, loblolly pine stands, and old-growth loblolly pines as well. And these are the planned ICESat2 track locations, 2 years of track locations over the study site. The inset map B shows a demarcation of 100-meter segments, so ATL08 again would be at these 100-meter segment scale. And the inset figure C shows these overlapping footprints, since ICESat2 produces these 70-meter nominal footprints every 70 centimeters along the ground track, resulting in these overlapping footprints. If we zoom out a bit, this is the closest ICESat2 transect to our study area. Again, we focus in that smaller area with planned ICESat2 track locations, but ongoing work involves using actual data along that ICESat2 transect. Just a quick overview of these methods. The simulation started with airborne LiDAR data, and the expected photon detection rate of ATLAS, the instrument on board ICESat2, was applied over temperate. This was temperate forest. So over temperate forest, we will expect 0, 1, 2, up to 3 photons per footprint. And as I guess Laura Duncanson mentioned earlier, it's less, but anywhere between 0 and 3, hopefully. But that's signal photons. To make a more realistic representation of the data, we added noise. Noise photons were added to the data. Noise photons are not discernible from signal photons, so further processing is necessary in order to derive the ground and top of canopy, and after that, canopy heights. So for the simulation, airborne LiDAR data was used, and then noise photons were added. The point cloud, although not shown here, the point cloud was processed using custom noise filtering and photon classification algorithms to retrieve the canopy parameters within the simulated data set. 100-meter segments were then extracted to be consistent with the ATL08 product, and several height metrics were calculated: height percentile, canopy cover, canopy density, and those were subsampled to address spatial autocorrelation that was observed. So the samples, the segments, 100-meter segments, were subsampled and then related to a reference airborne LiDAR-derived above-ground biomass using regression analysis. The prediction equation were then prediction equations, because this was carried out for 3 different data scenarios. They were applied to Landsat pixels, well, to segments and then to pixels, and upscaled using land cover maps and canopy cover maps, as well as vegetation and vegetation indices from the imagery. Using both, we use both deep neural networks and random forest for comparison. For the simulated data scenarios, again, 3 scenarios were investigated in the study. A no noise scenario, so estimated with an estimated 2 photons per footprint applied with no noise added. And then we also investigated a daytime scenario and nighttime scenario. Of course, less noise will be available in the nighttime scenario, and we see that with the actual ICESat-2 as well, the data with a lot less noise than its daytime counterpart. The data again was processed. The daytime and nighttime scenarios were processed using these custom noise filtering and photon classification algorithms. I include the citation for those that was done by Popescu and others, published last year. These figures, the 2 figures on your left, show the actual data, the raw photon-counting LiDAR, and processed data as well. This is for that nearby transect that I showed earlier near to the study area. The vegetation conditions are similar to that within the study site. So the equations that were developed with this simulated data have been applied to the actual data. That is still ongoing, so I won't present that today, but that is just some ongoing work. This allows for a visual comparison between the real ICESat2 data and then what we simulated on the right. That simulated data over the Sam Houston National Forest in Texas. Oh, and I should mention, so when it's processed, we retrieve this ground on top of canopy as well as canopy photons. And then the 100-meter segments are extracted and used for regression analysis. The reference above ground biomass, it was a map that was developed using both field inventory or ground measurements as well as airborne LiDAR data. Above ground biomass was estimated using output after the processing of the airborne LiDAR data and based on relationships between airborne LiDAR and field data. Above ground biomass was estimated for pines and deciduous hardwood separately using popular allometric equations. For the simulated photon counting LiDAR estimated above ground biomass, this is with the simulation, those segments were subsampled first, and then related with that reference above ground biomass map. The data was divided into training and test sets, and the regression models were developed with that training data. And this was published earlier this year for more details on this study. But overall, it achieved good accuracies between the simulated data and the reference above ground biomass. R² values range from 0.63 to 0.79 with the nighttime scenarios, for the study area. Once we had that regression equation, they were applied to all of the segments and then to Landsat pixels based on the proportion of a 100-meter segment across a pixel. We only use those pixels where at least 7 meter of a segment travels that pixel. These are a list of the predictive variables from Landsat imagery. We use Landsat 5 thematic mapper because of to avoid temporal mismatch between our data, our reference as well. For the image, as first a single scene was downloaded from Earth Explorer, processed in NV, and we calculated vegetation indices which are popular in the literature, NDVI, EVI, soil adjusted vegetation index, and the modified version as well. And they were combined with canopy cover, that's from the National Land Cover Database, and land cover as well. So a first set of models were developed with these predictors, and then a second set of models were developed with an extended dataset. The extended dataset consisted of the same vegetation indices calculated from a year of imagery. So the same NEVI, EVI, SEVI, and the modified version were calculated from every single image over a year of imagery for the study area Landsat imagery, and they were used to develop a separate set of models for comparison. For this study, we focus on only deep neural networks, essentially multi-layer, multi-neural networks. So learning basically is done via successive layers of representation all these models. We used Keras and R, so open DL frameworks for modeling above-ground biomass with deep neural networks. For the optimizer, which was RMS prop, which is popular for many different uses with deep neural networks, as well as the rectified linear unit as the activation function to enable nonlinear representations of the data. We looked at successively narrow architecture, beginning with a wide second, third hidden layer, and successively narrow layers. Layers were added based on predictive performance until there were so additional layers were added until they did not result in improved model performance. And we analyzed models as wide as possible, as wide as needed, and as in depth as many layers as needed, although many weren't. We also tuned the learning rate. In some studies, a higher learning rate may be okay or result in sometimes better results and lower learning rates. So we looked at a few different learning rates to see how well they perform. Just because the literature, it seems that there were limited studies involving regression, deep neural networks for regression tasks with estimating forest biophysical parameters. There are many classification studies, and in terms of regression-based tasks, there seem to be a limited number of studies. So we also looked at tuning the learning rate as well. And on to results, this is one of the resulting maps from the deep neural network. I believe this is for the nighttime scenario, but I'll talk a bit more on that in a bit. Okay, so with the final selected architecture, neural network architecture, you see with daytime, nighttime, and no noise scenario, no more than 3 hidden layers were needed. 2 to 3 is enough, but a bit wide, I guess. But there are significant or substantial differences in model performance with different learning rates, with better results, a lot better. For instance, 0.25 to 0.42 with lower learning rate. However, we don't need to go as low as possible. 0.001, for instance, was a decent value for learning rate in those neural networks. And of course, we got better results with our nighttime and daytime scenario. I think I have, okay. Here's a scatter plot of those results with those final neural network architectures. Essentially, it exhibits a common trend of underestimating biomass at the higher ranges and overestimating biomass at the lower biomass ranges. That's the common trend with all of them, which is more pronounced with the daytime scenario. Overall, with these, you can see the R² value ranging from 0.42 to 0.49, well, 0.50 with no noise, but at this point, realistically, it's the daytime and nighttime scenario. So 0.42, 0.49. So not so great R² values, but when we look at this extended data set, no data reduction techniques were examined here. We looked at the vegetation indices calculated from a year of imagery, resulting in 94 predictor variables. We get a lot better performance, model performance for each data scenario. I think, what does this mean? So daytime, you see 0.42 with just 6 variables, but when we incorporate all that phenological information from a year of imagery, NDVI, EVI, we get a lot better performance with the deep neural networks, and it's the same for each scenario. The same thing with, and of course, better RMSE values as well. And what we notice in this table is similar performance between random forests and the neural networks, which would mean probably might be possibly better with random forests, but because they're so similar, it may be important to examine both techniques as well as other deep learning algorithms as well. This was just one that was examined in this study, but there are many more that we could look at. And this is some of the ongoing work using the prediction equations from this area, apply those to this ICESat2 transect, and then upscaling, you can do wall-to-wall mapping. But again, it's very preliminary, and reference data would be very, very important in order to analyze to validate these results as well. So that is still ongoing. With the availability of ICESat-2 data and JEDI data soon, I think Dr. Dubai mentioned in November, we'll have both ICESat-2 and JEDI, as well as upcoming missions. We'll have lots of data to work with. So in that case, deep learning can be investigated more extensively as it can handle large, complex data sets. So we could examine a lot more deep learning algorithms, and given the similar performance between deep learning and random forest, both should be investigated as well as other techniques as well. And this study, while doing this study, there were limited examples of deep learning models for regression tasks with estimating forest biophysical parameters. So more of those would have to be explored. And now it's a lot easier to implement with open source deep learning architectures and frameworks as well, like TensorFlow. So they could be examined more extensively. And ongoing work involves the application of these methods using first linear regression for the segment level estimation of above-ground biomass, and then applying those to pixels, then wall-to-wall mapping. That's our overall workflow. It will be implemented with real data. And that's all. Thank you very much.